Hello everyone. Welcome back to our journey with triangles and geometry. Let me ask you something fun. Have you ever noticed how two photocopies of a document look exactly the same, while a reduced photocopy still looks like the same content but smaller? That's the difference between congruence and similarity. Two figures are congruent when they have the same shape and the same size, like two identical squares or two circles of the same radius. But two figures are similar when they have the same shape but not necessarily the same size. For instance, all circles are similar whether their radius is 2 centimeters or 200 centimeters, the shape remains the same. Similarly, all equilateral triangles are similar no matter the side length. Remember, every congruent figure is also similar, but not every similar figure is congruent. Congruence is like being twins, similarity is like being cousins who look alike but differ in height. Hello students, let me start with a curious question. Have you ever tried comparing a football and a dice? Or a coin and a triangle ruler? At first glance, they are all shapes, but are they really similar? This brings us to an important point. Figures of different types cannot be similar. For example, a circle compared to a square or a triangle compared to a square. Their shapes are fundamentally different. Remember, shape equivalence is mandatory. Just scaling the size up or down cannot create similarity if the shapes themselves are different. You can make a small square into a big square and they'll be similar. But a circle can never transform into a square, no matter how much you stretch it. Visual inspection often helps us reject such non-similar pairs quickly. You look at them and instantly know they don't match in shape. Take a simple example, a circle and a square. They lack common proportionality in both sides and angles. The circle has no straight sides, while the square has 4 equal sides and 4 right angles. Clearly, they cannot be similar. So here's the quick insight: similarity requires the same type of figure. Only triangles can be similar to triangles, squares to squares, and circles to circles. And that's why, before applying similarity tests, the first thing we check is whether the figures belong to the same family. In the next lesson, we'll see how triangles, in particular, give us rigorous criteria like angle, 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 and side, side, side to decide similarity. Stay tuned. Hello students. Let me ask you something interesting. Have you ever seen two shapes that look similar at first glance, but when you try to match them, something feels off? That's exactly why mathematics insists on formal rules for similarity, not just our eyes. Some figures may appear similar by eye. For example, look at quadrilaterals labeled ABCD and PQRS. At a glance, both shapes look alike. But if we go deeper, appearances can be deceptive. True similarity cannot be left to guesswork, it must be proven by rules. Here's a simple way to understand this. Imagine two photographs of the Taj Mahal, one small, one large. The shapes are identical, just scaled. That is true similarity. But now, take photographs of the same person at different ages, even if the size is the same. The face changes shape, proportions shift. They are not similar because the form itself has changed. So, the message is clear: similarity is objective, not just visual guesswork. We must use proportional sides and equal angles, not just what looks right to the eye. And this is why we need formal rules of similarity. They prevent us from being tricked by appearance and guide us with certainty. In the next lesson, we'll explore these rules step by step, starting with triangles, the simplest and most reliable shapes for proving similarity. Stay tuned. Hello students. Let's begin with a simple observation. Have you ever noticed how the same picture can appear on a postage stamp and also on a giant billboard? The size changes, but the shape remains exactly the same. That's the essence of similar polygons. So here's the precise definition. Two polygons with the same number of sides are similar if two important conditions are satisfied. Condition 1. Their corresponding angles are equal. For example, angle A equals angle P, angle B equals angle Q, angle C equals angle R, and angle D equals angle S. Condition 2. Their corresponding sides are in the same ratio. For instance, side A to B divided by side PQ equals side B to C divided by side QR equals side C to D divided by side RS equals side D to A divided by side SP. This constant ratio of corresponding sides is called the scale factor. Think of it like enlarging or reducing a photograph, 35:45 or 35:55. The shape stays the same, only the scale changes. To show correspondence clearly, we write it symbolically as A corresponds to P, B corresponds to Q, C corresponds to R, and D corresponds to S. Here's the key takeaway: equal angles plus proportional sides guarantee similarity. No guessing, no assumptions. It's a precise rule. And remember, similar polygons are like different-sized versions of the same figure. They are exact replicas in shape, just stretched or shrunk. In the next session, we'll focus on triangles because they are the simplest polygons and form the backbone of all similarity theorems. Stay tuned. Imagine you're looking at a blueprint of your dream house. Now, what if I told you that the size you see on that paper is not the real size? It's all thanks to something called the scale factor. But how exactly does this work? Let's dive in. Scale factor, also known as the representative fraction, is simply the ratio of the size of a drawing or model compared to the actual object. It shows how much the object has been enlarged or reduced to fit a smaller space. Think of it like when you shrink or enlarge a photo, but with precision. Have you ever used a map? Those world maps you see? Or maybe you've looked at architectural blueprints for a house or seen a model of a building. These all rely on scale factors. A map, for instance, has a scale like 1 to 50,000. That means 1 unit on the map is equivalent to 50,000 units in real life. The scale factor makes it easier to understand huge distances or sizes in a more manageable way. Now, how does the scale factor actually affect the size of an image? Well, if the scale factor is k, that means each side of the image will be k times the original size. So, if you have a scale factor of 2, your image will be twice as large as the real object. On the other hand, if the scale factor is less than 1, say 1/2, the image will be half the size of the original. It's a simple yet powerful way to represent objects in a more compact form. And that's how scale factors work. Whether it's for a map, a model, or a blueprint, the scale factor helps us fit big things into smaller, manageable sizes. So next time you're reading a map or admiring a model, you'll know exactly how those objects relate to the real world. In the next video, we'll dive deeper into how to calculate the area and volume using scale factors. Stay tuned. Ever looked at a world map and wondered how they shrink the vast world into a small piece of paper? Well, the magic behind that shrinking and enlarging of things is something called scale factor. It's not just limited to maps, it's everywhere. Let's break it down. A scale factor ensures the shape stays the same, even when it's resized. It's like having a blueprint of your house. You want to build it bigger or smaller, but the proportions should stay identical, right? Scale factor works like a special key. Imagine you've got a figure in front of you, could be a triangle, rectangle, or even a building blueprint. The scale factor helps you understand how much bigger or smaller the shape is without changing its proportions. Now, let's talk about how we calculate this. The formula for side ratios is AB divided by AB equals BC divided by BC equals K, where K is the scale factor. This constant K tells you how much the figure has been enlarged or reduced. Take a look at maps. You've probably seen something like 1 to 50 million. What this means is that one unit on the map represents 50 million units in the real world. So, the scale factor here is 50 million. Imagine if you wanted to build a model of the world using this ratio, it would maintain the same proportions, just a scaled-down version. With scale factor, you ensure that shapes remain identical even when their size changes, making it super useful in maps, models, and blueprints. So, next time you look at a map, think of the scale factor working behind the scenes to keep everything in proportion. Hello students, let's work through an example together. Imagine two quadrilaterals drawn, one larger, one smaller. At first glance, they look alike, but how do we prove they are truly similar? Let's find out step by step. We are given quadrilateral ABCD and quadrilateral ABCD. Our task is to verify their similarity. Step 1. Measure angles. We check that angle A equals angle A, angle B equals angle B, angle C equals angle C, and angle D equals angle D. When all corresponding angles are equal, the first condition is satisfied. Step 2. Measure sides and check proportionality. Now we compare corresponding sides. Side A to B divided by AB equals side B to C divided by BC equals side C to D divided by CD equals side D to A divided by DA. This equal ratio shows proportionality of sides. Step 3. Verification. If both these conditions are satisfied, equal angles and proportional sides, then quadrilateral ABCD is similar to quadrilateral ABCD. Symbolically, we write quadrilateral ABCD tilde symbol quadrilateral ABCD. Finally, the result and check. We verified similarity through equal angles and equal ratios. This proves they are similar by definition, not just appearance. So here's the key takeaway: similarity is confirmed by rules of geometry, never just by eye. And with that, you've seen how similarity can be tested step by step. Next, we shift focus to triangles, where these rules become the foundation for powerful theorems. Stay tuned. Hello students. Let me ask you something. Have you ever seen two objects that look almost the same, but when you check carefully, something doesn't quite match? That's exactly what happens when the formal conditions for similarity fail. Let's see an example. A square and a rectangle, at first glance, both have 4 right angles. So their angles are equal. But the sides are not in the same ratio. That breaks the rule of proportionality, so they are not similar. Now take a square and a rhombus. This time, the sides are in proportion, but the angles are not equal. Again, one condition is broken and similarity fails. This teaches us something very important: either condition alone is not enough for similarity. Both conditions, equal corresponding angles and proportional corresponding sides, must hold together. Quick insight: failing just one condition is enough to destroy similarity. Even if one part matches but the other doesn't, the figures cannot be similar. And here's another deeper thought. Congruence is just a special case of similarity where the scale factor is 1. So similarity not only generalizes congruence, but also extends geometric ideas to real-world applications like scaling models, maps, and even computer graphics. So remember, True similarity requires both equal ranges and proportional signs. If either one fails, the similarity collapses. In our next lesson, we'll see how triangles, the simplest polygons, give us very clean criteria for checking similarity. Stay tuned. Let's recap everything we learned. All circles, squares, and equilateral triangles are always similar. Definition: to polygons with the same number of sides are similar if corresponding angles are equal and corresponding sides are proportional. The ratio of sides is called the scale factor, used in maps, models, and architecture. Pitfall alert: satisfying only one condition is not enough. You need both. So, similarity means equal shape with proportional measure. And that's what connects mathematics with the way we build maps, photos, and even skyscrapers. In the next lesson, we'll see how these rules apply specifically to triangles and how we can set up clear criteria for triangle similarity. Stay tuned.